Okay, so first thing I've done here is define the function. So that's going to be the first thing we do nearly every time. Let's define the function f1 of x. Okay, I had a look at the graph to make sure it was the same thing. I need the coordinates of the stationary points. So given it's only worth 2 marks, the marks are going to be for the correct answers. So it's not crucial we show all the working out that we need here. So you can see here on the calculator, I've worked out where the derivative is equal to 0. So even if we type this, we need f dash of x equal to 0. So x is equal to 8 on 3 or 6. Now coordinates, people, which means therefore the coordinates are 8 on 3 substituted into the function. I get 500 on 27 and what's the other one? 6. And you can see from the graph there, it's at the 0.60. So be aware that this one here, if you've got decimal answers, you're not going to get it. Okay? The very first part of the exam says leave your answer as exact figures unless instructed otherwise. So if you've just traced this on your graph, okay, and if you trace it on your graph, I think you get 2.67 and 18.5. They are not going to get you the mark, all right? Exact values. So find the values of x for which the derivative is strictly less than 0. So where is the gradient of the line less than 0? So the gradient of the line is less than 0 through here. And obviously the turning endpoints are not going to be included. So we've worked out what our turning points are. So strictly less than 0 means I need x such that, what are we going to have? We're going to have 8 on 3 is strictly less than x, which is strictly less than 6, okay? Part C talks about the midpoint of the line segment joining the two stationary points. So put the two stationary points in, okay? And the line segment is just the line joining them. So it's that section there. You can see it's already on the calculator. And I need to find that point there. So what is the rule for the midpoint? Midpoint is equal to x1 plus x2 on 2, y1 plus y2 on 2, which in this case is equal to, what are my x values? My x values are 8 on 3 plus 6, which is 18 on 3, all over 2. The y values are 500 on 27 plus 0 over 2, which is equal to, what have we got, 26 on 3, which is all divided by 2, which is going to be the 0.13 on 3, and 500, 250 on 27. Now what we need to do is show that the 0.13 on 3 is in fact on the line. So if we work out f of 13 on 3, that is in fact equal to 250 on 27, and therefore so lies on the graph. Okay, so again, first thing here is just to find this function on your calculator, and I've done that, and I'll put up the screenshot for that in a minute. And so then if we just work out the derivative of that expression, I'm going to end up with, where is it here? I'm going to end up with g dash of x is equal to x minus a 3x minus a minus 2. Okay. For what values of a is the gradient of the graph of g at the point 1, 0. You have to excuse my printout. I've got all the pieces in it, so I'm going to work with yours as well. 1, 0 positive. So in other words, if I put x equal to 1, g dashed of 1 is equal to 1 minus a times 3 minus a minus 2, which is 1 minus a times 1 minus a 1 minus a squared. So it's greater than 0 if a does not equal 1. Now we could solve that on the CAS, and I'll show you that in a minute. The answers there from my screenshot. So what's part C saying? So the part C is saying we've got a point there, P and Q are some rational numbers, lies on the graph of G. Okay, so it's a part of the function. The gradient of the graph of G at the point P and at the point 1, 0 is equal. Find the values of P and Q. So straight away, if the point P lies on the curve, that means that G of whatever the point P is, so that's the point P times 4a minus 1. So that value there is equal to the y value, q times a minus 1 cubed. That's equation 1. All right. Equation 2 is about the gradients. So the gradient of my graph, so here's my gradient over here. So the gradient at the point 1, 0. Yeah. So that means that, so G dashed of P times 4a minus 1 is equal to the gradient up here at x equal to 1, which is just 1 minus a squared. So there's my two equations. I put them into my CAS and get myself an answer. And you can see from our calculator screenshot that we get some answers of Q equal to Q equal to Q equal to 4 on 27 and P equal to 1/3. Okay. All right, let's have a look at question F. The graph which is shown below, okay, for which A happens to be greater than 1 is shown below. Find the value for A for which the shaded region above the x-axis has the same area as the shaded region below the x-axis. All right, so we know from the graph of g of x, and we probably haven't put one in here just yet. Don't forget the equation of g of x is x minus 1, x minus a squared. So that's the point there, a, that's the one that's varying. This point there is 1. So what do I need to know? I need to show that the area below the line, so from 0 to 1 of g of x dx has to equal the area from 1 to a g of x dx. So that's what we're looking to solve, all right? So don't forget though that this has got to be a negative in some way because this area here is negative. So maybe I might go from positive 1 to 0, whatever the rule for g of x is, x minus 1, x minus a squared dx has to equal from 1 to a x minus 1, x minus a squared dx. There on the right hand side, if we put in the relevant integrals, okay, so as long as you've got the integrals correct with the terminal points, there's a mark each. A has got to be greater than 1, doesn't it? A has to be greater than 1, so therefore A is equal to 4. All right. Okay, so again, first things, windmill, we're talking about the blade of the windmill and how far they get above the ground, I think. The breeze moves the blade so that the height in meters of the point L above the ground is given by, where T is the time minute after the movement was first. Okay. Initial height. First thing I did was to find the function. Okay, it just doesn't take much, all right? I came up with 0 to 6 just because I thought, well, I just wanted enough periods to make sure that I get a couple of cycles in. If I need to change it later on, I can. But at least then when I go to solve, if I have to solve, I don't have to redefine anything. Initial height is at t equal to 0. And you'll see I put ft of 0 in. I got undefined out. I thought, well, what's going on there? And then I had a quick look at the interval that I defined for, and I didn't use an inequality sign. I just put, greater than or equal to. So redefined it, put f2 of 0 in, I get 7. So the initial height above the ground was 7 meters. How many minutes is L next in the height at this height above the ground? So that's my period, isn't it? And the period is 2 pi on n, which is 2 pi on whatever the n value happens to be, which in this case is pi. So it comes around every 2 minutes. What is the average rate of change? Have a look. Average rate of change. Okay, between from t equal to a half and t equal to 0. So as soon as you see the term average rate of change, we know it's y2 minus y1. So for 2 marks, I'm going to have to put in, I'm not going to put f in, I'm going to put h of 0.5 minus h of 0 over 0.5 minus 0. Now I could work out the top line, 3 over 0.5, which is equal to 6. What are my units? We're in meters per minute. Okay. Find h dashed of t. Okay, again, I'd use my calculator for that, but I'm not going to do the screenshot of that since we don't really need to. So my calculator, h dashed of t is equal to 3 pi sine pi t. Just be careful to put t in and not x, okay, if you're copying it off your CAS. What's the next part of it? It says, find the least value of t for which the rate of change of h is a maximum, i.e. rate of change derivative is maximum, which means really I need sine pi t equal to 1. Okay, and that's going to equal 1. Therefore, pi t has to equal pi on 2 because that's when sine is equal to 1. So if t is a half, all right, so after half a minute, my rate of change will be at its maximum. Okay, so let's have a look. We've got our water being pumped. So what's happening here? So we're going to have water going up, then into a down pipe, and then into a big cylinder. So first things first, we need to find the volume of the cylinder. So we know volume is pi r squared h. So what does that mean? There's the height of my cylinder, and I guess my radius is that distance there, isn't it? Right. So first things first, let's always consider that point there. That's the point x, and the y value is 10 minus root 100 minus x squared. Yeah. So this here is the height, which is the y value, which is that there. So that's the height. What's the radius? Well, the whole distance, that distance there is x. So that distance there is just going to be 12 minus x, isn't it? So my volume is equal to pi times the radius, which is 12 minus x squared, times the height, which is 10 minus the square root of 100 minus x squared. So if I just make sure I've got that written down right from the question sheet, that looks about right. So that P symbol, which hasn't printed out too well, it's obviously the pi symbol, isn't it? So I think in terms of a proof, I think we probably really need, because you could argue that all I've done is just rewritten the formula. So I think we need to state, there's a bit of working out here. So h is equal to y, which is equal to 10 minus equal to 10 minus the square root of 100 minus x squared, and the radius is equal to 12 minus x. Well, just maybe just something like that. The domain of V, so obviously the domain is just all those values for which our volume equation is defined. So clearly the radius, I've got a square root of 100 minus x squared in here. So absolute maximum, I'm going to need x, I guess the size of x to be less than 10. So what else? So we're going to say negative 10 is less than x, which is less than 10, but x is obviously not going to be negative. So the domain of V, that takes us to 0 and 10. Let's have another, are there any restrictions also on the size of the x value? Can it be slightly bigger than 0? So that looks about right. So little open dot there means we can't have 0. And I'm pretty comfortable with saying it's a closed bracket 10, because if x is 10, it just means we have a shallow or a flat container. All right. Part G, on the axis, sketch the graph of V against S. Well, this is just copying it straight off our CAS, isn't it? Okay, so we can see from the calculator image just at the end, we've got a few key values there, so 6.4228. So we'll pull that about there. 9.9118, so almost at 10. Okay, so our graph is going to go up, down, and it comes back again. And if we check at 40 pi, and 40 pi is, what is 40 pi? That's 40 pi is at the point 125. So at 10, 125, so it might stop about there. Okay, so everything like correct to one decimal place. So 6.422 8.2 0 0, turning point down here 9.9118.7, and the endpoint had to be in exact form 10 40 pi. So let's quick check. On the axis below, sketch the graph of V against S. Label any endpoints. Yes. Stationary points with their coordinates to one decimal place. Okay, no excuse for not getting that one. Hence, find the radius of the tank when the volume is at a maximum. So the volume max is at x equal to 6.4 to 2 decimal places. So we probably might need to carry a little bit more accuracy, 6.425. Therefore, the radius we said was 12 minus 6.425, which is 5.575. Okay. So those. Okay. Find the angle theta in degrees correct to 2 decimal places when the volume of the tank is a maximum. So if we go back to a little diagram, if I just do a quick sketch of it here, we're talking about there's the drain pipe there, yeah? And that's the angle we make. And we just discovered that this was 6.425, that's 10. So we've got opposite hypotenuse. So I could go sine theta is equal to 6.425 over 10. Theta is equal to, sine inverse of that, 39.978 degrees. 2 decimal places, therefore theta equals 39.98 degrees. So we want to know, so we know that if we go back to our diagram, there's my blade, if you like, here, L, and it says that our blade works in a anti-clockwise direction. So we need the time it takes, time to travel, what do we say? 39.98 degrees. All right. So what do we know about the time it takes for the blade to travel? Well, we know the period of the whole thing was 2 minutes, I think. So we needed to travel 39 degrees, or 40 almost, 40 degrees out of a possible 360. So what percentage? So we need to travel 39.98 out of 360 degrees times 2 minutes. And that'll give me 0.22210 minutes and 2 decimal places, which is 0.22 minutes. Okay. I don't think we need any calculation. All right. Manufacture mobile phones X and mobile phones Y. Time it takes for mobile mode and capacity charge is used for charge time. Okay. Model X are normally distributed. Okay, so model X are normally distributed with a mean of 1 and a standard deviation of 3. So 1 hour and 3 minutes. So I reckon let's change that to 60. So it's all the same time frame. Find the probability that a model X phone has been randomly selected from the clock pile, has a charge time greater than 62 minutes. So we need probability that X is greater than 62 is simply going to be equal to our normal CDF. I always forget which way we put this in. Or CDF. I'm going to go with 63, and I want from, if you like, 62. I'll put infinity as long as we have a suitably large enough number, and that's equal to 0.2525 to 4 decimal places. A second model X phone is randomly selected from the stockpile. After 1 hour of charging, it is not fully charged. Find the probability that this phone will be fully charged sometime after 65. So this is a conditional one, isn't it, really? So we're saying, what's the probability that the time it takes is greater than 65 minutes, given it's already greater than 60? Yeah, because I've been on the phone for 60 minutes and still hadn't charged. So from conditional, I know there's a probability that x is greater than 65 and x is greater than 60 over the probability that x is greater than 60. So it's got to be greater than 65 and greater than 60. So that's just the same as the probability that x is greater than 65 over probability that x is greater than 60. Well, no, greater than 60 is just equal to a half because that's the halfway point. The mean was 60. And x is greater than 65, we'll use our calculator for 0.04779. So on my calculator then, I'm going to get 0.0956. Okay. In fact, I've really broken one of my cardinal rules, haven't I? Just because I was in a rush. Let's put those values there, just so we've got an idea of the kinds of things that we can expect. A further 3 model phones are randomly selected from the stockpile. Find the probability that exactly one of these 3 phones has a charge time greater than 1 hour. So we've taken a sample of 3. What's the probability of it being greater than an hour? Probability greater than 60 is just equal to a half, isn't it? So that's my p-value. Exactly, so I need the probability that we have one of those phones take greater than 1 hour. So I have 3 trials. Probability of success is a half. Probability of failure is 2. So I actually just going to end up with 3 times 1/2 times 1/4, which is 1/8, which is 3/8. Doesn't say anything about decimal places, people. So I guess this is where it's a little bit, you've got to be a little bit careful. Go to my calculator and just use the binomial, I get 0.375. And I reckon for 2 marks, we're going to need the, we're going to need to have the exact form of it. All right. All right. It is known that 10% of the Model Y mobile phones that the manufacturer has in its stockpile have a charge time greater than 1 hour. So the probability that Y is greater than an hour is equal to 10%, which is 0.1. A large consignment of Model Y phones is sent to retail, which sells 32 of them on the first day they arrive. Find the probability of the correct 4 decimal places that at least one of these phones sold on the first day has a charge time greater than 1 hour. So it's a binomial, isn't it? We had 32 trials. Probability of success is 1/10. I want, what do I want? At least one? At least one. I want x is greater than or equal to 1. So the probability that x is greater than or equal to 1 minus probability that x is equal to 0, which is equal to 1 minus, well, we can use our CAS here and still get a decimal. So what am I going to only go with 32, is it? 32C0. Probability of success is 1/10. Probability of failure is 9/10. So it's just 1 minus 9/10 to the power of 32. Which is equal to 0.9657. to 4 decimal places, so that's fine. Okay, obviously, as soon as we have our decimal places, which I actually didn't read the first time, we can just go straight to our CAS calculator and put in our binomial thing. All right. So what you really need to do for 1 mark, just putting this, that's worth 1 mark. Well done. Okay. So to get 2 marks, there has to be something else. All right, which means it's identifying this information here. Okay, so identifying that it's a normal distribution with a probability of success of whatever. All right, this one here, 2 marks. Don't just put an answer. Well, it's a bit easier here because it's expected value and variance. Manufacturer decides to take a sample of 100 model Y phones from a number of different retail outlets supplied. Let what? Let P hat be the random variable of the distribution of sample proportion of model Y phones with a charge time greater than 1 hour for these sample of 100 model Y phones. So since we're finding the expected value and variance of P hat, not the distribution, so normally we just go E of X is equal to NP, and we'd have 100 times 1/10, which is 10. So that's the expected variance of the number of phones. We want to know the expected variance of the random sample, okay, of P hat, the random variable. So E of X is simply equal to P, which is equal to 0.1. And the standard deviation, the variance, is simply equal to 0.1 times 1 minus 0.1 over N, which is 100, which is equal to 0.1 times 0.9 over 100, which is equal to 0.0. One more O is there. That's enough. So obviously we're going to check those on our calc, aren't we? All right, what's the question say there? Find the probability. I want the probability that P hat is greater than 0.05 given P hat is less than 0.15. So we know from my rules that's the probability of the intersection P hat greater than 0.05 and P hat is less than 0.15 over probability of P hat being less than 0.15. So it's got to be 0.05 is less than P hat, which is less than 0.15 over P hat is less than 0.15. So what that means there is what? So we know what P hat is. So we need to work out really some corresponding values. So that's the same as probability that the number of phones Y, 5 is less than Y, which is less than 15, over Y is less than 15. Now the key to remember thing here is because we're looking at a binomial distribution, that's the same as probability that 6 is less than or equal to Y, which is less than or equal to 14, over Y less than or equal to 14. Yeah, because it's only whole numbers. I can't be 15, so I can only go as 14. I've got to be bigger than 5, so I can only be as small as 6. So if I just come over here, that's the same as my binomial CDF. What do we have? 100 trials. Probability of success is 0.1. 6 to 14 over binomial CDF 100 trials, 0.1, 0 to 14, which is equal to 0.9379. Okay, I know it's a little bit confusing, our proportion terminology, but we're just got to try and space it out, have a couple of examples that you can refer to try and help you along. What's part G? A particular retailer at the sample of 100 ml is taken found 12 phones which have a charge time of greater than 1 hour. Use this sample to determine a 90% confidence interval, correct to 2 decimal places. There are two things about it. It's worth 1 mark, so we're just looking for an answer. So we know N is equal to 100, P is equal to 12 out of 100, and I want a 90% confidence interval. So if I just go to my calculator and use the Z interval, so the Z interval 1 proportion, I've got 12 successes, 100 trials, and I want a 90% confidence interval. It's going to give me an answer of, to 2 decimal places, is it? To 2 decimal places, I can write that as 0.07 to 0.17. Okay. So what do we know? What is the probability? So the probability of X being greater than 60 minutes is equal to a half. The probability of Y being greater than 60 minutes was equal to 1/10. Okay, they were the earlier parts of the question. So a technician's the charge time is greater than 160, greater than 60, it will be repackaged as a Model X phone. So otherwise it's a Model Y phone. So if the charge time is greater than 160, so it's correct. Yeah. So for the technician to get it right, I need the probability that the charge time is greater than 160 and it's a X model. If both of those statements are true is okay, or I need the probability that the phone time, I probably should put time there, the charge time is less than 60 and it's a Y model. So I need both of those conditions to be true. So the probability of it being greater than 60 and an X model, it goes a half by a half, plus the probability of a Y model and also being greater than 60. So the probability that a Y model, getting a Y model is a half, because half the value, half the phones in the collection are Y model phones, and for the Y model to be packaged correctly, for it to be packaged as a Y model, it's going to be less than 60, and 90% or 9/10 of the phones are less than 60. So if we multiply those together, a quarter plus 9 on 20 plus gives me 14 on 20, which gives me a 0.7. Okay. Now, what's the next part asking us? Next part's asking us, all right, so the probability of, what do we need? A Model Y phone, given that the phone was packaged correctly. So from my conditional rules, we know that that's given by the probability of a Model Y phone and being correctly packaged over the probability of being correctly packaged. So the good thing is we've got the probability of it being correctly packaged already. That's the 0.7 from the previous question. Now, what's the probability of a Model Y phone being correctly packaged? Well, the only way it can be packaged as a Model Y phone is if the technician found the charge to be less than an hour, which means then the probability of him having that correct is, well, the Model Y phone, 50-50 chance, and 90% of all the Model Y phones are charging less than an hour, which means then he's got a 90% chance of it being right there. So what's that give me? A 0.45 over 0.7, 45 over 70. You can use your calculator there, but if I divide by 5, I get 9 over 14. Okay. Okay, so we've got the graphs of H and H inverse there. Find the intersection. Find the rule and domain and the rule of what? Of H inverse. So, easiest way, y equals 1 over x minus 1, which implies then we can put x equals 1 over y minus 1. X plus 1 equals 1 over y. Y equals 1 over x plus 1. So we can say then that H inverse of x is equal to 1 over x plus 1. The domain of H inverse, we know it's equal to the range of H. So the range of H is from -1 to infinity. So that's not so bad. All right, find the value of C, the point of intersection. So you can solve the inverse and the inverse and the function equal to each other, but it is much easier to solve one of them equal to x, okay? And you can do that straight on the CAS. So I might even just type that in now as we're doing it. Solve 1 over 1 plus x equal to x for x. We've got decimal. No, it just says find the values. So we get a positive and a negative value there. Clearly we want the positive value. So I get the point √5 minus 1 on 2, which means because it's the same point, it's the same value. All right. Find the integral from 1 to c of h of x dx. Where's h of x? C to 1. So we're looking at h of x. So it's just this little area here, isn't it? Yeah. So again, straight on the calculator. From 1 to √5 minus 1 on 2 of h of x. I'm going to put that into the CAS now. Then I get the natural log of √5 plus 1 on 2 plus √5 on 2 minus 3 on 2. Again, doesn't say anything about decimals, so we need the exact answer. Hence, find the area of the region bounded by the graphs of H and H inverse and the X and Y axes. So what does that look like? I reckon that's what this area here is, isn't it? So I reckon those two blue areas are the same. I haven't probably drawn that quite as well as I should have. I'm going to make it a bit bigger, because now hopefully you can see. Not with that, I can't. there. So those two areas are the same. We've just worked them out. And that area there is just a square. All right. So let's just scroll that page up a little bit. So my total area will equal 2 times all of that, natural log root 5 plus 1 on 2, root 5 on 2 minus 3 on 2. We can simplify that a little bit as 2 natural log root 5 plus 1 on 2 plus root 5 minus 3, plus that rectangular square, which is just equal to my C coordinate squared. So possibly I could put that into my calculator, try and tidy it up a little bit. Which is equal to, so we can see from the transformation, we're looking to try and draw some relationship between that K and that D value there. So hopefully we remember from our dilations and transformations that D value there, so X is equal to X dashed on D, Y is simply equal to Y dashed. So if I apply that into my original graph of H of X, so if I've got Y equals 1 on X minus 1, if I substitute those in, I'll get Y dashed is equal to 1 over X dashed on D. So Y dashed is equal to D over X dash minus 1. So clearly we can see that that D scale factor is exactly the same as the K factor. So K is equal, it's terrible. So D and K are the same, so let's put D is in fact equal to K. So what's the transformation that the D or the K value does? We're multiplying our X values, aren't we? So if we're multiplying our X values, it's dilated by a factor of K, and since our X values are being multiplied, it's from the Y-axis. We're going to do something similar, except obviously we've got a K involved there, so we just got to treat the K as if it was that number 1 or just a number. So we're going to find the inverse of the HK function. So for the inverse, swap X, Y. So I'm going to write instead X is equal to K over Y minus 1. So then X plus 1 is equal to K over Y. Y is equal to K over X plus 1. Therefore, HK inverse is equal to K over X plus 1. All right, the line L1 is the tangent to the graph of HK at the point where it crosses the x-axis. So here's my tangent line there. Okay, so let's have a look. When K equals 1, L1 and L2 represent the same line. So the two lines that we're talking about here That's one tangent line. That's the other tangent line. Okay, so tangent lines we know are about the gradient. Okay, so what's the gradient at those points? So if I work out the gradient of, what are our lines called? Of just our first line here. So if we work with the we just work with the y equals 1 on x minus 1 line, dy dx is equal to negative 1 on x squared. And if I work with y equals 1 over x, what have we got, x plus 1, dy dx is simply equal to negative 1 over x plus 2 squared, x plus 1 squared. So don't forget that these ones here, they're the k values, but we just said k was equal to 1, all right? So I've got a funny feeling that's going to become significant in the next part of the question. So where are my x-intercepts and y-intercepts? So that point there, if I put x equal to 0, I get the point 0, 1. And this point here, so we're looking up here on the graph now, if I put y equal to 0, x will equal 1. So they're the two intercepts for those particular graphs when k is equal to 1. All right. So if I want to work, I'll work in red for this tangent line here. Okay. Which is the inverse graph, which is this one here. All right. So I'm interested in the point at x equal to 0. I get 0 plus 1. The gradient is equal to negative 1. So I've straight away got y equals negative x plus some constant c. And the point I'm interested in is the point 0, 1. So at x equal to 0, y is equal to 1, I get c equal to 1. So the equation of that tangent line is 1 minus x. If I go to green, say, for this point here, so at this point here, there's my gradient. I'm interested at the point x equal to 1. And the gradient at x equal to 1 is equal to negative 1. So I've got y equals negative x plus some c at the point 1, 0. If I put the point 1, 0, y equal to 0, x is equal to 1, which means c is equal to 1. Y is equal to 1 minus x. Therefore, L1 equals L2 if k equals 1. Let A be the acute angle made by L1 and the x-axis, and by L2 and the x-axis. So let's stick to our green line. So my green line that's the angle there. And for my blue line, it's also the angle there. The acute angle is the smaller angle. So let's remember tan theta equals m, where m is the gradient, but it's also that angle there, okay? Which is there. So as x gets bigger, the inverse function is higher. So it's a bit hard to tell with the angle, so we'll call alpha, and we'll call that the inverse. I think that's the inverse, and I'll go theta, and we'll call that the function. Okay, so we know at x equal to, we know at k equal to 1, same gradient, okay? So if we just work with the general k value, if I work out the derivative of h of x, Okay, I get negative k over x squared, so that's the gradient. And if I work out h inverse of x, the derivative of those, so d dx, I get negative k over x plus 1 squared. The points that I'm interested in are the relative respective intercepts. So for the original function k on x squared, I'm interested in the point k0, which is where the intercept is at. For the inverse function, I'm interested in the point 0k. So if we substitute those respective points into my derivative, this means my gradient of my tangent line will be negative k on k squared, which is negative 1 on k. And in here, if I put x equal to 0, the gradient will be equal to just negative k. So you can see here straight away, so if k is equal to 1, so if k is equal to 1, the gradients are the same, which is what we discovered. M1 equals M2, if you like, equals negative 1. All right. Now, so if k is greater than 1, so let's just go, if k is greater than 1, okay, it means my m gradient, the green gradient there, which is, I guess, the inverse function, is greater than the original function. And if k is less than 1, that means my red function will be greater than my green one, which is the inverse function. Okay? So, yeah, it's a little bit of thought in that one. All right, what have we got to finish with? Is it to finish with, I hope? All right. P of x is some function h inverse of x minus h of x. Okay, so that's the difference between the two functions, isn't it? Find in terms of k, where's the rest of the question? The values of x for which p is greater than 0. Okay, so the key point is that point of intersection, isn't it? In terms of k. So straight away on my calculator, I'm going to solve what's it? K on x minus 1 equal to k over x plus 1, and I'll get x is equal to two possible answers, but we want the positive one, 4k plus 1 minus 1 over 2. Okay, so if we just go back to our graph now, that's the point of intersection. So the inverse function is bigger if x is bigger, so therefore p is greater than 0 if x is greater than square root of 4k plus 1 minus 1 over 2. Okay. All right, so here's just a little snapshot, a clearer snapshot of the graphing that we have in place here. So that's the line y equals k. Let's have a think. That's my h inverse of x function. And that's my, I'll put that in blue. And we'll say in green, there's my, there's my h of x function. Now we need to find the area of the curve, okay, in terms of p. So first things first, what is p? P is h inverse of x minus h of x. Yeah. So p in this instance here, the inverse is blue minus green. So given we're talking about areas, we're talking about top function minus bottom function. The area that we've been asked to find is the area bound by the graphs of h and h inverse and the line y equals k, which is this area here. Okay, that's the area we want. That's my point of intersection, which we worked out to be 4k plus 1 minus 1 on 2, repeated. K plus 1 minus 1 on 2. Yeah. That's k there. So that's y equal to k. So this is the equivalent from all our working out of where x is equal to k. So if I give myself a straight line here, from symmetry, I'll use a different colour, those two areas are the same, okay? Because they're the inverse of the function. Don't forget we're the line y equals x, so we're symmetrical about that line. So those two areas are the same. So what would this area in green be? Well, that area in green would be the integral from that first red point, root 4k plus 1 minus 1 on 2, to the point k of top function, which is the blue function, h inverse of x, minus the bottom function, which is the green function, h of x dx. Yeah, so that's what the area is, but we've been asked to give that in terms of p, or p of x, and p of x is simply that function there. So the equivalent statement would be root 4k plus 1 minus 1 on 2 to k p of x dx. Okay. Look, it's the last question on the paper for a reason. Okay, it takes a little bit of thought, and I know it's a challenge when we start dealing with p's and k's and everything everywhere. But look, if you can sketch a few graphs, pinch a few points here and there, that makes all the difference. All right, good work.